Hello everyone. Previous class we had discussed about scanning electron microscope as well as optical microscope. These are the characterization techniques. Today we'll continue with scanning electron microscope applications as well as limitations before we go on to next topic. So there are many applications. So first one, material science. Basically it is used for research applications in certain industries for quality control and failure analysis and material science industry as well. It has also application in semiconductor inspection where topographical information is gathered with the help of scanning electron microscope. Also microchip design and production is also possible with these kinds of scans. Next, third application is forensic investigations. So analysis of gunshot residues, jewelry examination, bullet marking comparison, handwriting and print analysis, examination of banknote authenticity, paint, particle fiber analysis, filament bulb analysis in traffic incidents. So next application is biological sciences, where we can measure the effect of climate change of species by studying the species in a micron level or nano level, identifying new bacteria and virulent strains, vaccination testing, uncovering new species, work within field of genetics. Next application is medical science, where we can identify new viruses as well as we can identify new diseases, testing new vaccinations and medicines, comparing tissue samples between patients in a control and test group, testing samples over the lifespan of a patient. So these are the brief applications of scanning electron microscope. So what are the limitations we'll study now? Basically scanning electron microscope is very expensive and it is housed in an area free of any possible electric, magnetic or vibrating interference. Maintenance involves keeping a steady voltage currents to electromagnetic coils and the circulation of cool water, because primary electrons are little bit elevated at a temperature. Special training is required to operate an scanning electron microscope, limited to solid inorganic samples, some small components which can fit enough in the vacuum chamber, and certain components which can sustain the vacuums produced in the microscope. These are the components which can reflect, which can produce the secondary electrons such as metals and other elements, can be used to be scanned by scanning electron microscope. Non-organic organic materials do not reflect or do not produce secondary electrons. In such a case, sputtering technique is used to coat that material with a metallic element such as gold, copper or any other element which can produce the secondary electrons, or can be scanned by using scanning electron microscope. Scanning electron microscopes carry a small risk of radiation exposure associated with the electrons that scatter from beneath the sample surface. Now we will see how actually scanning electron microscope works with a physical video of the equipment.
The scanning electron microscope. Scanning electron microscopy is one of the most fascinating examination methods. This video shows how it works in practice. Main components of the microscope are column for electron beam generation, specimen chamber, vacuum pump, monitor, and control panels. The material tester turns on the vacuum pump control and vents the specimen chamber. After pressure equalization, she can open the cover plate of the specimen chamber. Together with the cover plate, the stage pans forward. Now different specimens can easily be placed on the round stage. the filament of an old used light bulb, part of a welded tube on a sample holder, a small cobalt plate, and a golden piece of jewelry. All specimens are assembled and we are ready to start. The material tester carefully closes the cover plate and switches on the two-stage high vacuum pump as well as the electronic control. It takes about 3 minutes to obtain a sufficient vacuum in the specimen chamber and column. Meanwhile, she turns on the monitor, initializes the motorized stage and boots the microscope control. Only now she is allowed to switch on the high voltage and the thermionic cathode. For the first time, a reasonable image appears on the monitor. It shows part of the specimen stage. Using the trackball, she moves the stage within the microscope. She looks for the place where the first sample is positioned, the used filament. The magnification is gradually increased. The position readjusted, and the magnification increased again. Now a plastic and high contrast image of the filament can be seen on the monitor. Originally, the coiled filament was quite smooth on the surface. Caused by the everyday use of the filament, new crystals have been formed. Tungsten atoms have evaporated and the outer regions of the filament have become polygonal. But how is this plastic image generated, and how does the microscope actually function internally? The animation first...
So you have seen how an image is generated by using scanning electron microscope. In comparison with optical microscope, this can generate high precision images without diffraction of the light. So right now you are seeing an image of a tungsten filament where it is zoomed or enhanced at around 1000x. That means 1000 times the original component it has been enhanced. So by this we will end scanning electron microscopy. Next part we will move on to the next characterization technique, that is transmission electron microscope. In comparison with scanning electron microscope, transmission electron microscope is much more similar to SEM, but with slight amount of changes. This differs in construction. I'll show the image how the TEM is constructed. So basically some of the components will remain same as we have seen in scanning electron microscope. For example, electron gun. Electron gun is used to produce primary electrons. Electromagnetic lenses are used so that we can divert the primary electrons at a particular angle so that they can be allowed to pass through a particular specimen, so that that specimen is to be analyzed or magnified. Here the component or the specimen is transparent in nature in comparison with SEM. SEM uses opaque kind of component where the reflection or generation of secondary electrons will be gathered to generate an image. Here in TEM, that is transmission electron microscope, these electrons are allowed to pass through a particular specimen and they will move on to a viewer or a recorder where the image is recorded. So basically in construction it is similar to SEM. Slight modifications are there. Specimen holder is a copper grid placed in between the objective lens and the electron gun, where while passing through electromagnetic coil, the electrons are converged at a particular point on the specimen. Through the specimen the electrons pass and move through the electromagnetic coil to the viewing area or the recorder. So basically It is a beam of electrons which are passed through an ultra thin specimen, interacting with the specimen as it passes through. When electrons are accelerated up to high energy levels and focused on a material, they can scatter or backscatter elastically or produce manual interaction sources of different signals, such as X-rays, Auger electrons, or light. Some of them are used in transmission electron microscope. So an image is formed in the interaction of electrons transmitted through the specimen. So this image is transferred or detected by a sensor such as CCD camera or a photographic film, which will record the image of the enhanced sample. There are different modes of imaging in transmission electron microscope. So first one, that is bright field imaging, is generated by passing the electrons, primary electrons, through the specimen and to the fluorescent screen, which is shown in this diagram. So here, uh, when the electrons hit the thicker part of the specimen, they will be distracted. They will be not allowed to pass through the specimen, and darker structures are formed on the fluorescent screen. In a similar manner, whenever the lighter elements of the specimen are there, it will allow the movement of electrons through the specimen and on the screen. So that means more electrons are passed on the screen, so that brighter image is generated. So thicker the specimen, darker image; lighter the thickness of the specimen, brighter image is generated. So this mode is obtained by intentionally excluding all diffracted beams and only allowing a central beam to pass through the specimen. This method is useful to study the microstructure of the samples in plane view and number of multi-layers from cross-sectional view. Next one is dark field imaging. As the name indicates, thicker sections or dark sections of the specimen are uh, uh, imaged in dark field imaging. Here, the diffracted beams are chosen to pass through objective diaphragm, so that they can pass through the specimen and reflect the same on the fluorescent screen. Here, uh, a central beam is objected, or is not allowed to pass through the equipment, so that we can generate a dark field image. The last method is diffraction mode. Here we are intentionally excluding central beam and we are collecting all the diffracted beams. As you can see here, central beam is excluded and other diffracted beams are being passed through to the fluorescent screen, which are passed through the specimen. So these three techniques are used in transmission electron microscope, so as we can generate a particular image of our requirement. We will now see what are the applications of transmission electron microscope. This is ideal for a number of different fields such as life sciences, nanotechnology, medical, biological, and material research, as well as forensic science, genomology, and metallurgy, as well as industry and education. This also provides a topographical, morphological, compositional, and crystalline information. This is also used in semiconductor analysis and production and manufacturing of computer and silicon chips. Technology companies use TEM, that is transmission electron microscope, to identify flaws, fractures, and damages to micro-sized objects. Limitations include it is large and very expensive, laborious sample preparation, because accurate sample is to be prepared so that we can analyze the sample correctly. Otherwise, the image generated will be disrupted. Operation and analysis requires special training. Samples are limited to those that are electron transparent, able to tolerate vacuum chamber, and small enough to fit in the chamber. TEM requires special housing and maintenance. And lastly, the images are black and white, just like scanning electron microscope. Now we'll see an animated video which will show how a transmission electron microscope works, and also the new advancement in the TEM process. The white portion you see here is the specimen, and the red color indicates the electrons being produced and passed through the specimen. The image is generated on the screen that you can see, where the atoms are darker in the electrons will not pass through the atoms, so that portion will be darker, where between the atoms there will be gap. In that gap, through that gap electrons will pass, that will be lighter. So like this image can be generated. The previous process is first method of generating an image. This process is process where the object or the sample is moved from one place to another place to be scanned. In this process, beam is shortened. The diameter of beam is shortened so that each atom can be scanned individually. This time process can also be altered so that we can generate a colored image of the object based on topography or based on the thickness of the component. We can consider higher thickness red in color, lower thickness blue in color. Between variation of these colors, we can produce a particular image by variation of the angle of the image produced. This completes the transmission electron microscope. Next, we will move on to the next characterization technique, that is Xray diffraction. Xray diffraction or X-ray power diffraction is a rapid analytical technique primarily used for phase identification of crystalline material and can provide information on unit cell dimensions. Phase identification we have already studied in material science, where whether the material is amorphous or crystalline based on the orientation of atoms, based on the orientation of grains, can be analyzed. So the working mechanism of X-ray diffraction method is very simple. Basically, we are using an X-ray source. The X-ray source will produce the rays, and that is passed through the collimator. Through the collimator, the rays are diverted at a particular angle, and sample is placed at a particular orientation where these rays will hit the sample. The process works by the X-ray hitting a particular electron of a particular atom, where new X-ray is generated with the same intensity as the previous X-ray, which is being hit, which is hitting the atom. That X-ray generated will be again moving at a particular angle, and that is detected by counting detector. So based on this, particular peaks are quantified. So those peaks will determine what kind of material, what kind of orientation particular sample has. You can see in this image where incident X-rays are passed at a particular angle, and those will hit the electrons of a particular atom. Here we can see in this image, two atoms are placed at a particular distance of d. Between that distance, an incident ray of X-ray will pass and hit an electron, and again X-ray will be generated by the electron from the electron of that atom, and that is reflected or diffracted at a particular angle, which will be collected by a collector. Now we'll see a video which depicts the working of the X-ray diffraction method.
What is X-ray diffraction, and what is it used for? In an X-ray diffraction experiment, a sample is placed into the center of an instrument and illuminated with a beam of X-rays. The X-ray tube and detector move in a synchronized motion. The signal coming from the sample is recorded and graphed, where peaks are observed related to the atomic structure of the sample. Most materials are made up of many small crystals, like sand on a beach. Each of these crystals is composed of a regular arrangement of atoms, and each atom is composed of a nucleus surrounded by a cloud of electrons. It's at this scale that the story of X-ray diffraction begins. X-rays are high-energy light with a repeating period called the wavelength. Since the wavelength of an X-ray is similar to the distance between atoms in a crystal, a special interference effect called diffraction can be used to measure the distance between the atoms. Interference occurs when X-rays interact with each other. If the waves are in alignment, the signal is amplified. This is called constructive interference. If the waves are out of alignment, the signal is destroyed. This is called destructive interference. When an X-ray encounters an atom, its energy is absorbed by the electrons. Electrons occupy special energy states around an atom. Since this is not enough energy for the electron to be released, the energy must be re-emitted in the form of a new X-ray with the same energy as the original. This process is called elastic scattering. In a crystal, the repeating arrangement of atoms form distinct planes separated by well-defined distances. When the atomic planes are exposed to an X-ray beam, X-rays are scattered by the regularly spaced atoms. Strong amplification of the emitted signal occurs at very specific angles, where the scattered waves constructively interfere. This effect is called diffraction. The angle between the incident and the scattered beam is called 2 theta. In order for constructive interference to occur, the scattered waves must be in alignment, meaning that the second wave must travel a whole number of wavelengths. In this case, 1/2 of a wavelength is traveled on the incident side, and 1/2 on the scattered side, yielding 1 additional wavelength. In the case of the next X-ray, 1 wavelength is traveled on both the incident and the scattered side, resulting in 2 wavelengths. This reinforcement occurs throughout the crystal. The exact angle at which diffraction occurs can be determined from the red triangle. The angle at the top is theta, half the angle between the incident and scattered beams. The long side is the distance between the atomic planes, and the short side we know is 1/2 of a wavelength. The relationship between the diffraction angle and the spacing between the atoms can be determined by applying the sine function. Rearranging this equation yields an equation commonly known as Bragg's law.
Now we'll see the actual equipment, how X-ray diffraction machine works.
Brugger D8 focus X-ray spectrometer is used to measure the crystal structure of powders or thin film materials. The X-rays are produced in an evacuated tube similar to a cathode ray tube. An applied current heats up a tungsten filament which liberates electrons. The liberated electrons are accelerated by a high voltage and hit a copper target where copper X-rays are generated. The X-rays exit the tube and are incident on the sample from which they are diffracted into a scintillating type detector. The beam passes through a slit which determines the angular width of the beam. Wider slits give more energy but have wider peaks. Smaller slits give less energy but better resolution. The beam also passes through a nickel filter. The nickel filter removes the K-beta energy before the diffracted beam enters the detector. X-rays at angle theta are reflected from internal crystal planes separated by distance d. The Bragg diffraction results from constructive wave interference when the quantity 2d sine theta is an integral number of wavelengths. A fine powder material contains many crystals located at random angles. Certain crystals happen to be oriented so that the X-ray beam, crystal, and detector satisfy Bragg's equation. This causes a signal spike at specific detector angles. It is important to have a sufficient number of crystals to have an even distribution at all possible crystal orientations. During a scan, the detector is rotated over a range of angles to detect bands of diffracted X-rays produced by the correctly aligned crystals within the sample. So now we're going to discuss sample preparation. For X-ray diffractometry, powder diffraction, it is important to have a well-defined polycrystalline material. And the individual particle sizes of your material should be below 45 microns. You need enough to fill one of these wells, and it should be packed in. And what is important is to have individual crystallate plane so that when the beam hits it at a particular angle, Bragg's equation is satisfied and you get a peak. Because, as I said, the more particles that you have represented on this surface in all of the various crystal planes, the better your data gets prepared properly. You're welcome to come in and use our sample holders. And you want to make sure that it's filling the well, but it's still flat with the surface of the sample holder. And you just gently scrape off whatever comes out of the well. Keep in mind, you're going to put this in, and there's going to be 3 pins on 3 places on the sample holder. And if there's a lot of material underneath there, that's going to actually alter the angle that it's sitting at, and you'll get your positions will be off. Just flatten it down. To verify that you have that, just kind of tip it up at a 45-degree angle and make sure that it's very accurate. The plane of the sample must be the same as the plane of the sample holder that is defined by 3 pins. Once your sample is loaded, you can close the doors. The doors are leaded glass and are part of the safety circuit in the instrument. So we are generating X-rays, and those are radiation and could be dangerous. Radiation doesn't travel very far, doesn't travel through thick objects, and it doesn't travel through lead. So these are leaded glass, and they have little pins in the handles that will engage mechanical switches in this right in here in the door. And then there's also electronic switches in the door in the bottom and the top. What this does is ensures that when you close the door, all the switches have engaged correctly and that the door is correctly closed. And then the sample ID now is changed to demonstration. It's loaded, automatically loaded my start and stop and increment values, and it's running the scan. And it moved the stage and the detector automatically, so everything is being done automatically. We can see there's a number of peaks already. This is Illumina, which is a NIST standard. This, right now, it's just drawing lines. If I right-click in here and select dots, I can actually see the data points. And hopefully you can see right away that this would not be something that would be recognized in analysis software. There's only one data point here. And you really want a minimum of at least 3 on its way up and it's on its way down. So that click indicates that it's finished.
So we have seen physically how this X-ray diffraction works. So now we'll discuss some of the applications. Basically, it is used in pharmaceutical industry where composition of particular materials are to be determined, forensic science, geological applications, microelectronics industry. Some other applications include characterization of crystalline materials, identification of fine-grained materials, determination of unit cell dimensions, measurement of sample purity. There are certain limitations. Homogeneous and single-phase material is best for identification. Must have access to standard reference or inorganic compounds. Requires at least some amount of material to be tested, some 1/10 of the gram. For mixed material, detection limit is 2% of the sample. For unit cell determinations, indexing of patterns or non-isometric crystals systems is complicated. Peak overlay may occur and worsen for high angle reflections. So by this we have completed X-ray diffraction method. Thank you.